Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. We have talked in depth about limits. We know it's about how functions behave as x approaches a value, not at that specific value. But we spent so much time in pre-calculus learning about how functions behave at a value, we're not going to just toss that out the window now that we've moved on to calculus. This leads us to an important idea we haven't touched on yet: continuity. The goal of this video is to use the foundational learnings of limits to create a definition of continuity so that we can be more precise with our mathematical reasoning. So let's take a look at these three graphs that we have on the screen here. Each of them has a discontinuity. In the first graph, there is a hole right over here. In the second graph, we have a vertical asymptote. And then in the third graph, we have a jump. All of these are discontinuities. We call the first one a removable discontinuity. Removable because it's as if we removed a point from the graph. The second one is what we call an infinite discontinuity because we have a vertical asymptote. And then the third one is a jump discontinuity because, well, it's pretty self-explanatory. There is a jump. However, these are not very precise terms, nor are they mathematical. So we're going to use limits to generate the formal definition of continuity. Now let's take a look at what that is. We say a function f of x is continuous at a point x equals a if all three of the following conditions are satisfied. And the three conditions are: a has to belong in the domain of f, and the limit of f of x as x approaches a has to exist. And not only does it have to exist, it has to equal to f of a. So in other words, the limit has to equal the value of the function evaluated at x is equal to a. So let's take a look at that first three graphs that we started with. For the first one, it is not continuous because if this is our a, then the limit of our function f of x as x approaches a does not equal to f of a because we have a hole here. In fact, we don't even know if a is in the domain because we don't see a y value for a anywhere on this graph. But even if, let's say, the point was somewhere up here, then it's still discontinuous because the limit is not equal to f of a. Now for the second graph, because we have a vertical asymptote there, it's discontinuous because a is not in the domain. And for the third graph, again, if this is our a value, this is discontinuous because the limit of our function f of x as x approaches a does not exist. And the reason that it does not exist is because our left side limit and our right side limit are different. So now using this more rigorous definition of continuity, we're able to show why each of these graphs is discontinuous. And now let's go ahead and take a look at an example. We're asked if our piecewise function f of x is continuous at x is equal to 1. So using the definition, we know that it has to satisfy all three conditions. And the conditions are: 1 is in the domain. That's our first one. The second one is that the limit as x approaches 1 of our function f of x has to exist. And then the third condition is that the limit as x approaches 1 of our function f of x must be equal to the function evaluated at 1. So now let's take a look at each of these conditions. The first one says that 1 has to be in the domain. And this is true because we can see that the function is defined at x is equal to 1. So we can put a check mark here. Our second condition says that the limit as x approaches 1 for our function must exist. So if we look at our piecewise function, we can see that the limit as x approaches 1 for our function is going to be equal to, so we can see that this function is defined as x squared when x is not equal to 1. So when we're approaching 1, regardless if we're approaching from the left side or the right side, we're going to be using x squared. And here we can just use direct substitution, and we can see that this is equal to 1. So we can put a check mark beside this one as well because the limit does exist. And then the third and final condition says that the limit has to equal to the function value. Well, we already found the limit in the previous condition. We found that the limit is equal to 1. So what is the actual function value? Well, f of 1 is equal to 3 because it's defined as 3 when x is equal to 1. So now we can see that they're not equal to each other because this one is 3 and the limit that we found earlier was equal to 1. So therefore, we're going to put an x beside the third condition. So since it failed to satisfy all three conditions, we would say that our function f of x is not continuous at x is equal to 1. For our next example, we have another piecewise function. So we're going to do the same thing. We're going to list out the three conditions that we need to check. The first one is that 2 is in the domain because our a value here is 2. The second condition is that the limit as x approaches 2 for our function, which is g of x, must exist. And then the third and final condition is that not only does the limit has to exist, the limit as x approaches 2 must be equal to g of 2. So for our first condition, we can see that g of x is equal to 5 when x is equal to 2. So it is defined at x is equal to 2. So we're going to put a check mark here. The second one is that the limit as x approaches 2 for our function g of x must exist. So now if we look at our piecewise function, we can see that it is equal to 2x plus 1 when x is less than 2, but it's equal to x squared plus 1 when x is greater than 2. So this tells us we're going to need to use this expression for finding the left side limit, and then we're going to need to use this expression to find the right side limit. So let's go ahead and find each of them. So the first one is going to be the limit as x approaches 2 from the left-hand side for our function g of x. So because we're approaching from the left-hand side, we're going to be using the expression 2x plus 1. So now using direct substitution here, we can see that this is equal to 4 plus 1, so that'll be equal to 5. Now the limit from the right-hand side, we're going to be using the other expression. So that's going to be equal to the limit as x approaches 2 from the right-hand side of x squared plus 1. Again, we can use direct substitution. So 2 squared plus 1, that's going to be equal to 5. And now, because we have the left-hand side limit is equal to 5, and the right side limit is also equal to 5, we can say that the limit does exist. So limit as x approaches 2 of our function g of x is equal to 5. So we're going to put a check mark beside this one as well. And then finally, the last condition, we need to compare our limit and the actual function value. Well, g of 2 is equal to 5 as defined by this part right over here. And that is equal to the limit that we just found. So therefore, this condition is also satisfied. So since all three conditions are satisfied, we can say yes, it's continuous at x is equal to 2. So now if you recall, when we talked about limits, we talked about one-sided limits. So for a continuity, there is something similar. We say that a function is continuous from the right at x is equal to a if the right side limit of our function f of x as x approaches a is equal to f of a. And we say that a function is continuous from the left at x is equal to a if the left side limit of our function is equal to f of a. So again, going back to the three graphs that we started with, neither the first graph nor the second graph have that one-sided continuity, but for our third graph, we can see that f of a is right over here. And it is equal to the limit as x approaches a from the left side. So for our third graph, we can say that this one is continuous from the left. However, it is not continuous from the right because the limit from the right side is over here, but f of a is over here. So this is not continuous from the right. Now, lastly, the functions that you've seen in pre-calculus, so functions such as polynomials, rationals, trig, exponentials, and logs, are all continuous on their domain. So given this information, and the fact that f and g are continuous functions at x is equal to a, then the arithmetic combinations of these functions are also going to be continuous at x is equal to a. The only disclaimer here is that for division, our denominator g cannot be equal to 0 at x is equal to a. So now let's do a recap of what we covered in this video. We introduced the formal definition of continuity. It says that a function f is continuous at x is equal to a if all three conditions of the definitions are met. And those three conditions are that a has to be within the domain, the limit as x approaches a for a function must exist, and lastly, not only does that limit have to exist, it has to equal to the function value evaluated at x is equal to a. We saw that discontinuities occur when one of these conditions fails, and it can be classified either as a removable, jump, or infinite discontinuity. We saw in our example how piecewise functions sometimes require checking continuity at the breakpoints using left-hand limits, right-hand limits, and the function value. We learned that continuous functions behave predictably, and the sums, differences, products, and quotients were defined of these continuous functions remain continuous. And now it is your turn to give this a try. Can you find the value of k such that this piecewise function here is continuous at x is equal to 1? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on limits and continuity in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.